if I'm here, say, that I'm more than halfway away from the peak here. So half of one of these sides corresponds to just a quarter of the whole thing. So I could go up a quarter of a unit over, and that would still keep me on that side, right? I can always stay on the sides by either going up or down. If my x is close to the top, I go down. If my x is close to the bottom, I go up. If it's dead on the bottom, I go up. If it's dead on the top, I go down. It's okay. I can stay on that side no matter what if the max size of the step is 1 over 4 to the n plus 1. Because it's a small step relative to the picture. It's 1/4 of the total sawtooth base. Okay, do we see this geometrically? So I don't know whether, given the x, I don't know whether I have to go down or up, but I do know that I could do either, and after I do that and take the difference, I'll either have plus or minus the step size, right? You know, if this thing is plus and I go up, then I'm beyond and I take away where I was and I get plus. If I go down, then I'm behind, right? And I take the difference and I get a negative. Is this clear? If it's plus, I go up the hill, take away where I was, and I get plus the delta m. If delta m is negative to begin with, I go downhill, take the difference, and get minus delta m. Okay. All right. So now, what would happen if instead of using m here, I use some other function, but still subtracted after I bump this thing up by delta m? Well, two things can happen. First of all, you notice if you're fiddling around here on a sawtooth edge, and either an up or down swing, you are always completely below a sawtooth edge from a prior function. It's like if I move on one of these, I never encounter a breakpoint. I never encounter the tip of a sawtooth from an earlier lower index function, right? Why is that? Because the breakpoints are first the powers of a fourth and the powers of a 16th and the powers of a 64th, right? So if I move around here for all the prior functions, there's only two in the drawing here, I stay completely below one of the branches. Now if I were over here moving around on this one, this middle one here, right? And say I'm moving up and down here, I would still be completely underneath one branch of a sawtooth or any prior index function. Yes? It's like an umbrella. Once you're here, all the prior ones are already over top of you because you're a quarter as big as the next one, and a 16th as big as the one before that. So they're all dominating you, right? No matter where you are. What's that mean? It means that if k is less than or equal to m, then you still get that. Because you're still, if I move up here, the delta m, if I move from x to x plus delta m, I slide up here, slide up on this one, slide up on this one. Never go over a peak. So that's true, right? What happens if k is greater than m? That's a function that is at least f sub m plus 1, but you're taking a step of size 1 over 4 to the m plus 1. And The next function up is periodic with period 4 to the m plus 1. So if I take a step size 1 over 4 to the m plus 1, where does it put me? The periodicity lands me at exactly the same height that I was. The thing repeats. The thing repeats with exactly the step that I say that I'm going to take. I'm going to take a step of size 1 over 4 to the m plus 1. The function f sub m plus 1 is periodic and repeats with period 1 over 4 to the m plus 1. So if I take the difference between a point x with the period added minus, this is like the sine, it's like, sine of theta plus pi over 2 minus sine of theta. It's periodic, theta plus 2 pi minus sine of theta. This is the period of everybody m plus 1 and beyond. So if I'm greater than m, that means m plus 1 or beyond. This is periodic. And what's this thing going to be? 0. If k is greater than m. So this difference is plus or minus delta m if k is less than or equal to m by construction, and 0 if it's greater. 0 because of the periodicity. If the step is taken and I look at a k that's less than or equal to m, I'm not taking advantage, as it were, of the periodicity, and I just move up one of the sides of the sawtooth. I either move up or down, and then my net difference, since it's it's either the diagonal or anti-diagonal, it's small. If I move over a certain amount, I move up the same amount, right? If I move over and on the downside, I come down minus the same amount that I went over. So this is true. This is true if k is less or equal than. This is true if k is greater. Can we accept that? See the reasoning? Amanda, you with me on this? I'm walking around here on this sawtooth, and if it's a tiny, tiny one and it's periodic, if I move from here with a periodic amount, I wind up at the exact same height because of the periodicity. So if I take the difference between here and here, it's 0. If the index of my function is low compared to the delta m, then I'm doing something like this. I'm moving a little here on the diagonal, main diagonal. If I move over a certain amount, I move up the same. If I'm on a downswing, if I move over a certain amount, I move down that. So it's either plus or minus the amount I move on the lower index points. 0 on the higher index. Okay, now, you see where I'm going with this? F of x. F of x plus delta m minus f of x. Okay, let's do this one. I'll just put the m's back in for a second and divide by delta m. What do I get? Plus or minus 1? If this was plus or minus delta m and I divide by delta m, I get plus or minus 1. True? That is if this is the basic m, and then we can write the same thing for k. So f sub k of x plus delta m minus f sub k of x over delta m is plus or minus 1 if k is less than or equal to m, 0 if k is greater. But that looks kind of like a derivative expression, doesn't it?